Hello, we are going to start our discussion of chemical equilibrium, which is chapter 13 in your text. And this really is the topic that we use throughout the rest of the class, the concept that we're going to be focused on. So we'll talk about what it means to have chemical equilibrium, how you know you're at equilibrium, and then we'll go through several chapters on examples of equilibrium. And one of our last chapters will be on the physics of the whole process. So we're going to switch from how fast reactions go to when do they stop changing. So that's the concept of chemical equilibrium. So okay, so this is chapter 14 in the new edition, but chapter 13 in your edition. So chemical equilibrium. So it's the state reached when the concentrations of reactants and products remain constant over time. So it's easy to measure experimentally. So for example, when we have this reaction of dinitrogen, can't think of the word right now for 4. So N2O4 going to 2 NO2s. At some point, the reaction is going to stop happening. So if we start with just N2O4, it will react to form NO2. Not necessarily every molecule will react, just depends on the equilibrium constant. So this is a picture of some experiments that were done on this reaction. So on the left-hand side, what you notice is you've started a reaction where you only have N2O4 and you have 0 NO2. And over time, their concentrations change. NO2 goes up, N2O4 goes down. And you notice whatever the time units are here, after one time unit, one quadrant of your graph, things reach equilibrium. So the concentrations stop changing. So in the initial point where it's changing, we call that the kinetic region. And then once the concentrations stop changing, that's the equilibrium region. You could start the reaction the exact opposite way. So on the right-hand side, you started the reaction with only the NO2 and 0 concentration of N2O4. You'll still reach a point at which the concentration stops changing and you're at equilibrium. And we'll be able to define that point as we learn more about the process. So this equilibrium state, I mentioned that the early time when the concentrations are changing, we call that the kinetic time, or the kinetic part of the reaction. And so the rate forward and the rate backwards aren't equal to each other. When they reach the point where they're equal to each other, then you're at equilibrium. So this is just the concentration data, and what you'll notice is, doesn't matter where you start, the experiment 1, 2, up to 5 starts with different concentrations of the N2O4 and the NO2, but in each case, the concentration of N2O4 and NO2 don't necessarily reach the same point, but something that does is the ratio of the products over the reactants raised to their stoichiometric coefficient. So you notice the equilibrium constant expression, which is products over reactants raised to their stoichiometric coefficients. That does reach a constant value. So that's the new constant. In the last chapter, we were focused on rate constants, lowercase k. Now we're going to be focused on capital K, which we'll call the equilibrium constant. So the equilibrium constant for any generic reaction. So the reaction given here on this slide, you could write the equilibrium constant as each concentration of product raised to the stoichiometric coefficient divided by each concentration of reactant raised to its stoichiometric coefficient. So for the reaction that we're looking at, that would be NO2 squared divided by N2O4 concentration. And you notice they point out that this is at 25 degrees because equilibrium constants depend on temperature. So just like rate constants, their values change with temperature. So when we look at this set of data, we've already noticed this, that even though the concentrations themselves don't reach the same value if you start with different concentrations for your experiment, but that ratio does. So in each case, the ratio is 4.6 within the certainty of our experiment times 10 to the minus 3. So if we write the equilibrium constant for any generic reaction, you notice the first one has one product, but its stoichiometric coefficient is 2. So the Kc for that first reaction is the ammonia, the NH3 squared, divided by nitrogen to the first power and hydrogen cubed. So if you look at each of these, you'll see how easy it is to write an equilibrium expression. If you notice the difference between the first reaction and the second, they're just written backwards. And so if you think about how you would write this, now the products over reactants will be the inverse of what it was when you had written it in the opposite direction. So the Kc prime for that second reaction is really just 1 over Kc for the first reaction, because the only difference in these two reactions is that one's going forward and one's going the opposite way. So in the next one, the difference between 1 and 3, they're going in the same direction, but you've multiplied all the stoichiometric coefficients times 2. So that means now it'll be ammonia to the 4th, nitrogen squared, and H2 to the 6th. And so if you compare that back to the equilibrium constant for the first reaction, it's going to be that equilibrium constant squared. So if you balance the reaction differently, you'll have a different numerical value for the equilibrium constant. So you can also write the equilibrium constant in terms of pressures. So if everything is in the gas phase, you could write a Kp instead of a Kc. The Kc was trying to indicate that it's an equilibrium constant written in units of concentration. But pressure is related to concentration. And so you can also write a Kp, the equilibrium constant in terms of pressure, and it has the same format. It's the product's pressure raised to the stoichiometric coefficient divided by the reactant's pressure raised to the stoichiometric coefficient. So this equation just comes out of the ideal gas law. So if you remember, PV equals nRT. N over V, number of moles divided by volume, is equal to the molarity. And so if you write that down, you can quickly see where this relationship comes from. So this comes from taking every concentration and converting it to a pressure through the PV equals nRT. So the book goes through that derivation and you should look at it. It's really simple. And the delta N is the difference in number of moles of gas in the reaction. So gaseous products minus gaseous reactants, their stoichiometric coefficients. R is the gas constant, T is temperature, and I just said delta N is the difference in the moles of gas in the product side minus reactant side. So you can always write a Kc, you can write a Kp if your reaction is taking place in the gas phase. This relationship wouldn't make any sense if you were talking about an aqueous reaction, because then PV doesn't equal nRT. That's only true for gases. So for heterogeneous equilibrium, so a reaction like this one, where you have limestone, calcium carbonate, going to form calcium oxide and carbon dioxide, the solids really have a constant concentration. You might have a different quantity, but the concentration is really just equal to their densities. So you can incorporate those into the K. So the only thing that you'll put into the equilibrium expression then is the concentration of CO2, the gas. So solids and liquids don't go into the equilibrium constant because they're really just constant concentrations at their density. So this is just showing you what a heterogeneous equilibrium might look like and how the quantities of the solids might be different. But as long as they're present, notice that you have the same equilibrium pressure of CO2, even though the pile of red calcium carbonate is much bigger on the left-hand side, the calcium oxide, or on the right-hand side, and the calcium oxide is much smaller. So this is just showing you that it's their concentration, not the quantity present. And so you reach equilibrium at the same pressure of CO2. So using the equilibrium constant, you can think, if you look at this first reaction, and we're going to do this reaction in the last week of class when we play with fuel cell cars, which use hydrogen gas. Notice that water going and splitting, it's through the process of electrolysis that you can force this to happen, because it doesn't want to happen. The equilibrium constant is 10 to the minus 48. So if you were to put the pressure of hydrogen squared times the pressure of oxygen divided by the pressure of water squared, you would basically have 0. It really doesn't go forward. So a really small equilibrium constant means you have mostly products or mostly reactants. Then you have something that's in the middle, something like in the lower left-hand corner, hydrogen and iodine, going on to hydrogen iodide, equilibrium constant 57. So that means you have a fair amount of both reactants and products when you reach equilibrium. Then when you get down to the lower right-hand corner, you've just reversed the upper left-hand corner. And so this should have an equilibrium constant of 1 over the equilibrium constant for the first one. But it really shows you when the equilibrium constant is 10 to the 47th, almost everything is on the product side. You have very little hydrogen and oxygen. So you'd get that concept whichever way you wrote the reaction, that in that reaction, you pretty much just have water at equilibrium. So using the equilibrium constant, I would like you to take a break right now. Go to page 498 and work problem 13.3. So it's within the reading on page 498. So take a break, do that problem, see if you want to glance over anything and make sure you've understood things to this point, and then come back and I'll be still here. So when you use the equilibrium constant, it's often convenient to use something called the reaction quotient. So notice that the reaction quotient looks exactly like the equilibrium constant instead of the T is in there, just meaning that it's the concentration of reactants and products at any time, which might not be equilibrium. So the reaction quotient QC is defined in the same way as the equilibrium constant KC, except that the concentrations in QC are not necessarily equilibrium. So if you think about that, if QC is smaller than KC, then you need to make the numerator bigger and the denominator smaller. So the reactants need to go on to form products. So if you calculate a QC and it's smaller than KC, you know the reaction has to go from left to right to reach equilibrium. If it's the opposite, if QC is bigger, then you need to decrease the numerator, increase the denominator to make Q smaller so it reaches a value of K. And so things are going to go from right to left, products to reactants. When you reach the point where QC equals KC, you've reached equilibrium. So this is just showing this in a more visual way when you think about the relative values. So QC smaller than KC, reaction goes forward. QC bigger than KC, reaction goes backwards. And you'll always reach the point at which they're equal to each other because reactions are always going to equilibrium. So let's just look at this problem where you can use the equilibrium constant. So they tell us the temperature because the value of the equilibrium constant depends on the temperature. You may not need the temperature in your calculation, but you need to know you're working at a temperature at which you have the equilibrium constant for that temperature. So it says 0.5 moles of HI is added to a 2-liter container and it's allowed to come to equilibrium. Calculate the equilibrium concentration of everything. So it gives you a KC of 57. Okay, So this just shows you, you can look at the flow chart in the book. I think logically you'll find your own way to do these problems. You can do them in terms of Q. It's not necessarily necessary, especially in this problem, because if you only start out with product, then the reaction has to go backwards, because no equilibrium constant is going to be infinity. So we set up this thing which is called an icebox. So initially we have 0, 0 for the reactants and 0.250 for the product. So as the reaction takes place, for every 1 H2 and 1 I2, we'll call that X, that's formed, you use up 2 HIs. So the reactants go up by plus X and the product goes down by 2X. And so at equilibrium, you should have X of each reactant, and you should have what you started with, the 0.250 minus 2X, as the quantity or the concentration of HI at equilibrium. So you have the value of 57. You're going to plug that in and plug in the product's concentration, 0.250 minus 2X squared over X squared, and then you just have to solve for X. And we will do that using Mathematica. Maybe I'll do that right now. I think I can open Mathematica. Just take me a second. So Mathematica is an awesome software package. It's very expensive, but the college has a license so that you can each have it on your own computer. So I'll just show you quickly how I could solve that problem for X. So in Mathematica, and you'll be able to play around with this and then use it on the test, you always capitalize every command. So I want it to solve this equation. And the equation is the one that we just had, 0.25 minus 2 times X, all squared, divided by X squared. And this one would have been pretty easy to solve without doing this, because we could have just taken the square root, but why not just look at Mathematica? So that equals 57, and that was a double equal. I'll do that again for you. You have to say equals equals 57, and you want to solve for X. And then in Mathematica, shift return gives you the answer. So can one of those answers work? So it's a quadratic, so one of them won't be physically possible, and it will be the second one, or the first one that's not physical possibly, because it's negative. So the answer for X should be 0.0261 or 262. So unless I type something wrong, let's go back and see what the book got. So here was the problem. And that was what I put into Mathematica. And yes, indeed, we got the same answer. Notice this one would have been a lot easier because both the numerator and the denominator are squared. We could have taken the square root. But you got a quick look at how easy it is to use Mathematica. So with Mathematica, you could solve a cubic or any higher order. So you don't have to freak out if you can set up the equations in this class. You can always use Mathematica to solve them. So our value of X, by our definition, if we go back, is equal to the concentration of H2, and it's equal to the concentration of I2, but 0.25 minus 2X is the product concentration. So that's what this is showing you. So now we have the concentration of all three species when we've reached equilibrium. This is just a picture of the reaction between nitrogen and hydrogen, making NH3. It's a really, really, really important reaction because NH3 is ammonia, which is used for fertilizer. So a lot of energy goes into making NH3, and this is just showing you a schematic of how that process works in industry. So now I want you to take another break, turn to page 511. So page 511 has two examples on it, 13.11 and 13.15. 13.11 and 13.15. So just take a little break, work those two problems, and make sure you're understanding what we're doing, and then come back and I'll still be here after you take a break. So now that we've learned something about equilibrium, know that this truly is the only concept in the rest of the class. So if you've understood it, things stop changing at a point, we call that point equilibrium. You will be able to think your way through any problem, even if we didn't cover the rest of the chapters in the book. So an important idea, which really is just an idea you could figure out logically, it's called Le Chatelet's principle. And it just says if you have a system at equilibrium, but you stress it, then the reaction is going to occur in a direction that relieves that stress. So some of the stresses are you could change the concentration of reactants or products. The volume or the pressure could be changed, and the temperature could be changed. So here we are. On the left-hand side, we have an equilibrium situation, QC equals Kc, for the reaction to make ammonia. And then we stress it. We add some nitrogen. So when we add some nitrogen, the K does not change. The equilibrium constant stays the same. But by adding some nitrogen, we've made the denominator bigger, and that makes our Q smaller than Kc. So we know that means the reaction has to go forward, and so we'll make more NH3 and use up some of that N2 and H2. So in this case, the K stays the same, but the reaction has to shift the concentrations in order to get the ratio back to being equal to the K. So in general, when equilibrium is disturbed by the addition or removal of a reactant or product, Le Chatelet's principle predicts that the concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance. So that just makes sense. The ratio was equal to Kc. You've added either more product or reactant, and that has to shift in order to consume some of that to take the value of Q back to K. The concentration stress of a removed reactant or product is relieved by net reaction in the direction that replenishes it. So our reaction's at equilibrium, we pull out some of the product, the reaction will have to go forward in order to make Q get bigger and reach the value of Kc. So this is just a problem that will work through that idea. So an equilibrium mixture contains 0.5 molar nitrogen, 3 molar hydrogen, and 1.98 molar NH3. It's disturbed by increasing N2 to 1.5. So our K is 0.291. So if we increase the concentration of the nitrogen, it's going to go into the denominator, and the denominator is bigger, therefore Q now is smaller than Kc. And we learned this at the beginning of the chapter. If Q is smaller than Kc, reactants will react forward from left to right. So you can really just look at the reactant and think about it. If you look at the reaction given, if you add more nitrogen, the stress of that added nitrogen, if you're already at equilibrium, will be relieved by reacting forward and using up some of that nitrogen. Changes in concentration. This is just a picture of what we've just been talking about. Changes in pressure and volume. So if we have a gaseous reaction like this, and we have 4 moles of gas on the reactant side and 2 moles on the product side. If we take a reaction at equilibrium, as is shown in A, and we decrease the volume, if you decrease the volume, you're going to increase the pressure. If you increase the pressure, it wants to relieve that pressure, and so it's going to react to go to the side that has fewer moles of gas. So it's going to react forward until you get more NH3, and that will decrease the overall pressure. So in general, just like concentration, you can think about the general changes in pressure and volume. If you disturb an equilibrium, Le Chatelet's principle predicts that if you increase the pressure by reducing the volume, you'll bring about net reaction in the direction that decreases the number of moles of gas. If you just happen to have a situation where you have 2 moles of gas on each side or equal number on each side, then nothing can relieve the stress, so the reaction won't change. But if you do have a difference in the number of moles of gas, it will react in such a way to decrease it. If you decrease the pressure by expanding the volume, the opposite's going to happen. The pressure goes down, relieve that stress by increasing the pressure, so you're going to react in the direction that increases the number of moles of gas. So this is the same reaction, and we disturb it by reducing the volume by a factor of 2. So if you reduce the volume by a factor of 2, then you're dividing each of these by 2. So the 1.98 divided by 2, reducing the volume, divided by 0.5. So in each case, we're reducing the volume, so increasing the pressure, and that will mean that our equilibrium constant now is greater than QC, and so if QC is less than KC, more reactants will be consumed, and the net reaction will go from left to right. So you can think about it conceptually, but you could also do the math and actually put the numbers in. So you could see if you had 2 reactants and 2 products, then you'd be dividing each by the same change in volume, and so KC wouldn't change, or QC wouldn't change. So if you change the temperature, now the value of K will actually change. And so in this case, this is showing you a graph of how K changes in this particular situation. So the K will either go up or down based on if the reaction is endothermic or exothermic. So for this reaction, it's exothermic, it gives off heat. So if you were to include heat on the reactant or product side, you'd put it on the product side. So if you increase the temperature and the heat's on the product side, you're adding stress on the product side by adding more heat. And so you're going to drive the reaction backwards, and the equilibrium constant is going to go down. So as the temperature increases, the equilibrium shifts from products back to reactants, if it's exothermic. So the equilibrium constant for an exothermic reaction decreases as the temperature increases, and it's the opposite if it's endothermic. So if it was endothermic, you could think conceptually that the heat's on the reactant side. So if you raise the temperature, you add more heat, wants to alleviate that, and then it would go forward. So an endothermic reaction, you can think of the heat is a reactant, and so if you increase the temperature, that reactant goes up and you want to relieve that stress, so it will react forward, it will consume some of that heat. This is just showing you a picture of how the equilibrium shifts when you have a different temperature. So either hot water or cold water, you have a different color, and the brown color indicates, which is it? Can't remember. I think it's the NO2 that's brown, but I'm probably wrong. Should tell us which is brown, which is why it's getting more intense. Okay, so time for another break. So take a break on page 516. Page 516, there's a problem 1316. On page 520, there's another problem 13.20. So take a break and do those two problems, and then come back and we'll finish the chapter. So on page 516, problem 16. On page 520, problem 20. So the last thing we have to talk about is what happens when you add a catalyst. So we learned about catalysts in the last chapter. They find a different route from reactants to products. And so they make reactions go faster by lowering that activation energy. But notice in this picture, they don't do anything to the relative energy of the reactants and products. And that's what's determined by equilibrium. So you can catalyze a reaction. It won't shift equilibrium at all. It'll just make you reach equilibrium faster. And there's one more problem I want you to do. So look over that section, and it compares the equilibrium constant to rate constants. So on page 524, there's a problem 23. Do that as your last problem to make sure you've understood the whole chapter. And I will come back in a little while and do a lecture where I work through a few problems for you.